Hello and welcome everyone. In this lecture, I will be discussing about secondary critical speed and shaft carrying multiple rotors. We will find the critical speed for multiple rotors. First, secondary critical speed. The main or primary critical speed is observed due to the effect of centrifugal force of unbalanced mass. Whereas in case of horizontal shaft, earlier we discussed about the vertical shaft. Now here it is the case of horizontal shaft. Apart from the main critical speed, large amount of vibration are observed at the half of the critical speed due to effect of center of gravity of rotor. This is the center of gravity of rotor, and this effect has been noticed in horizontal shaft only and totally absent in case of vertical shaft. The important and severity of this secondary critical speed is very much less than the main or primary critical speed. Let us consider with an example. Suppose this rotor is rotating in anti-clockwise direction. Now the torque on rotor is due to the gravitational force mg, which is acting toward downward direction, m into g. When the G lies on the right side of the center O and accelerate the shaft when the point G is on the left side of the O. What will happen? When the G is on the right side, the mg will retard the shaft, which means it will try to reduce the shaft motion. But when the G is on the left side, it will accelerate. Gmg will accelerate the shaft. So here you can see when the G lies in the right side, the acceleration is in the mg is in this direction, while G is on the left side, the mg is on the opposite side. So the magnitude of this varying torque acting on rotor due to gravitational force can be found as T. Torque, we know that torque is equal to force into perpendicular distance. So here the eccentricity over here, which is E, and this angle over here it is also E, and this is angle omega t. So this is the horizontal component, this is our vertical component. We have to torque will be the horizontal component, which means this is the mg into mg cos omega t into E. So due to the variation of the torque, rotor will retard, which means from minus 90 to plus 90, and accelerate from plus 90 to 70, which means from this point to this point it will retard, and from this point to this point it will accelerate. The angular acceleration or retardation is can be found from this equation. Alpha is equal to T upon I, where I is the mass moment of inertia of rotor. Hence, the tangential acceleration or retardation at the point G is given by Ft is equal to alpha into E. Now, the tangential force will be mass into acceleration. So, this is our acceleration value. We put in this equation, we will get the tangential force. So, from here we can see that another figure, the vertical component of tangential force is acting in this direction, and this is the vertical component of tangential force, which is F cos omega t, that we can find. So this is the final answer, which is for the vertical tangential force. From this equation gives the force acting at point G, which is vertically downward direction, and the first part of above equation, which means the if we multiply this part in this and this with the this portion, this will be the first part. So the first part is due to this first part is constant, m we know, g e I we know, and causes small additional deflection of shaft. And the second part we have 2 omega t, which is variable part and having frequency 2 omega, and hence if the shaft is running at speed of omega n by 2 or omega c by 2, half of critical speed, the variation of vertical force occurs at the frequency omega n or omega c. This lead to resonance condition, and hence large amount of vibrations occurs. This effect is called as half frequency whirl. So this was the secondary critical speed. Now let us discuss about the critical speed of shaft carrying multiple rotors. For this, consider a shaft having negligible inertia and carrying multiple rotors. Let the M1, M2, M3, M4 be the mass of each rotor, and Y1, Y2, Y3 and Y4 be the corresponding deflections. The critical speed of shaft carrying number of rotors can be determined by two methods. First one is Rayling's method. So this method is based on the principle of kinetic energy is equal to the potential energy. Ke is equal to Pe. The maximum kinetic energy is given by the, we know that the kinetic energy is equal to 1/2 mv square. So here for rotor, suppose velocity is v1 for m1 mass rotor, for m2 mass it is v2, m3 mass it is v3, m4 mass it is v4, we can write down the maximum kinetic energy by this equation, by adding all the kinetic energy of all rotors. Now here it is written that y1 omega c, as we know that the linear velocity v is equal to r omega. This is the equation. But over here we, instead of r there is y deflection, and instead of omega there is omega c, which is the critical speed. So here it is y1 omega c, y2 omega c, y3 omega c, and y4 omega c. For number of rotor we can add. So in general we can write down this here 1 by 2 omega square omega c square. Critical speed is common for all because the all rotor are mounted on the same shaft. So by generalizing we can give kinetic energy by this equation. Same way, potential energy, maximum potential energy, we know that the potential energy is 1 by here mgh. Instead of h there is a y deflection, y of shaft. Here the height will be equal to y1. So the potential energy will be 1 by 2 m1g y1. For second rotor it will be 1 by 2 m2g y2. For third rotor it will be 1 by 2 m3g y3. Same way for multiple rotor we can write in generalized form. The g and 1 by 2 is constant, so we take it outside. We can write sigma 1 to n mi by I. So this is the maximum potential energy. But we know that according to Rayleigh method, the maximum kinetic energy and potential energy are equal. So by comparing these two equations we will get the omega c, critical speed or natural frequency, omega c, critical speed of shaft omega c in radian per second. Now for that we can find the natural frequency. Natural frequency is equal to omega c upon 2 pi. So this is the final equation of natural frequency for shaft carrying multiple rotors. For that we require the mass, y deflection to find the critical natural frequency. Next, second method to find critical speed of shaft carrying multiple rotor is Dunkerley's method. Here the critical speed of shaft carrying multiple rotor or number of point load along with uniform distributed load is obtained by Dunkerley's formula, empirical formula. Empirical, which is derived from the experiments. Here the shaft carrying several point load with uniformly distributed load. So for each we will get 1 upon omega c square is equal to 1 upon omega c1 square plus c2 square, same way up to cs square. So what is omega c? Critical speed of shaft carrying number of point load and uniformly distributed load, while omega c1 is the critical speed of shaft neglecting its mass and all point load except load 1. We will consider only load 1. Same way for cs, the critical speed of shaft considering its mass and neglecting all point load. Now consider a shaft carrying several point load with uniformly distributed load as shown in figure. Let the delta 1, delta 2, delta 3 be the static deflections of shaft due to load W1, W2 and W3 when considered separately. Delta S is the static deflection of shaft due to self weight or due to uniformly distributed load. Now we know that natural frequency of transverse vibration or critical speed due to W1 omega 1, we know that there is omega is equal to, we have two equation, under root k by m or it is equal to under root g upon delta. So here we use the equation under root g upon delta 1, which is for load W1. Similarly, we can find the natural frequency of transverse vibration or critical speed due to load W2 and W3 by these two equations. There is change of delta 2 and delta 3. The natural frequency of transverse vibration or critical speed due to uniformly distributed load or self weight of shaft is given from this equation. Now the static deflection due to point load for simply supported beam is given by, here suppose there is only one W load, static deflection, due to, this is our suppose simply supported beam with a point load W. The distance is L1 and L2. What will be the deflection? Deflection will be equal to W L1 square L2 square divided by 3 EI. This is the equation of deflection for point load of simply supported beam. But same for static deflection due to uniformly distributed load for simply supported beam. If the load is UDL, W per meter, so the static deflection is given by 5 W L raised to 4 divided by 384 EI. Here it is the L length. This is the equation for static deflection due to the uniformly distributed load. where I is the moment of inertia of shaft, which is equal to pi by 64 d raised to 4. So this is the two methods for finding the critical speed for shaft carrying multiple rotors. Now let us discuss one example. A shaft of 50 diameter and 3 meter length has a mass of 10 kg per meter length, and it is simply supported at end carrying three masses m1, m2, m3 at radius distance 1 meter, 2 meter and 2.5 meter from left support. Find the natural frequency of transverse vibration. Assume E 200 into 10 raised to 9 Newton per meter square. So this is, we can draw using this diagram, simply supported at end and carrying 3 mass. So first of all we have to find the static deflection for mass m1. So for mass m1, this will be the our L1 and this will be our L2. So using this equation we can find the static deflection, and for m2 this will be our L1 and L2. Same way for m3 this will be our L1 and this will be our L2. So using same equation, mg L1 square L2 square upon 3 ei L, we can find the static deflection due to mass m1, due to mass m2 and due to mass m3. Now static deflection due to self weight. For self weight, the value of self weight is given over here. The self weight is given 5 into 10. So 10 is the self weight. So what will happen? Due to static deflection, here mass of ten kg per meter. So we can find the static deflection due to self weight 5 by this equation, 5 times mg, or we can say w, L raised to 4 upon 384 ei. Now we have to find the natural frequencies due to individual load. So omega c1 is the critical speed for shaft 1 carrying mass m1 and its static deflection is delta 1. So we can find, same way we have the all value of delta 2, delta 3 and delta s due to static deflection. So we can find the all angular speed, and using Dunkerley's formula we can find the ultimate critical speed and natural frequency for the same. This is fc. So this is it for today's lecture. Thank you very much for watching.